Hey guys, hope everybody's doing okay. What we're going to do today is take a look at double replacement reactions, and we'll learn how to predict products for those and write something called an ionic and net ionic equation. So anytime you have a double replacement reaction, this is the process you should go through. We'll walk through it from beginning to end, then you'll be able to do some practice problems and hopefully complete a double replacement lab if we've gotten that far in class. So we want to start off with looking at what it means to be dissolved. So when an ionic compound dissolves, it dissociates into separate ions. So the key word here is dissociates, and you have something like potassium chloride, KCl, and you put KCl into water, and it's going to dissociate like this. And what you end up with is a potassium ion and a chloride ion. So that is really important. It dissociates into ions. Okay, so we have our initial KCl piece here, right? And then when it dissociates, the charges show up. All right, so there are no charges when it's combined, and then when it's separate in water, when it dissociates, we have the charges that show up. So what holds an ionic compound together? Ionic compounds are held together by something called electrostatic attraction, and that is simply the attraction of opposite charges. So you have K plus 1, Cl minus 1, and of course we know by now opposites attract, and they come together. All right, so the attraction of opposite charges holds that compound together. However, when you mix an ionic compound in water, we have water molecules in play now, and that does something to that ionic compound. So when, again, ionic compounds are in water and they dissolve, it dissociates into separate ions because of the water molecules taking an important role in that process. So there it is, dissociating again. Let's see why that happens. The charged ends of the water molecules are also attracted to the charged ions, and it pulls them apart. So I know you learned a little bit about water in biology, and you probably learned that water is polar. And water has basically two separate ends to it. We have a positive end where the hydrogens are located, and we have a negative end where the oxygen is located. So you can see the water molecules here on the slide, and I put little positive signs where the hydrogens are and a negative sign where the oxygen is. So using our rule of opposites attract, we have our positive end, our negative end of oxygen, right here, negative end of water, is going to be attracted to the positive ion. And the positive end of water, where your hydrogens are located, that's going to be attracted to the negative end of KCl, our negative ion. So let's see what happens there. We have our opposites being attracted. Okay, again, oxygen side is negative, being attracted to the positive ion in KCl. And we have our hydrogen side of the water molecule being positive, and that's attracted to our chloride. Okay, what's going to happen then is in water, that attractive force between the oxygen and the K plus 1 and the hydrogens and the Cl minus 1 is pretty strong. It actually pulls it apart like that. All right, so we are pulling apart our ions. All right, so again, potassium and chloride being separated because our water molecules are surrounding these ions. Now we have more than one water molecule doing this. The K plus 1 would be surrounded with a little hydration shell of water molecules, and the chloride ion, again, surrounded by a hydration shell of water molecules, just with different parts of the water molecule being attracted to those ions. So if we want to represent an ionic compound that is dissolved in water, something like this, I want to represent salt water, we could do it two different ways. So NaCl, dissolved in water, okay, our ions separate. We have Na plus 1 ions and Cl minus 1 ions floating around. Since it's in a water solvent, right, we want to just write NaCl with a little AQ next to it. We talked about this back when we talked about an introduction to chemical equations and what these symbols mean. So AQ, again, means it's dissolved in water, that's aqueous. It is not the same as NaCl liquid. Remember we talked about this. NaCl liquid is molten salt, okay, very, very hot, very, very hot to melt it. NaCl is simply salt water, salt dissolved in water. You're typically going to see it written this way on any sort of bottle or label in our chemical reactions as well. There is another way to show this, though, which is an Ionic formula. So the Ionic formula is when you just show what the two ions are in solution. So you have Na plus and Cl minus. Now, if you do have something like this, where you have, let's say, you had magnesium chloride, where you had MgCl2, you could write it this way, MgCl2 aqueous. All right, that's one way to write it with your formula, knowing magnesium chloride is dissolved in water. Your ionic, though, is going to be a little different. You have Mg plus 2, and then you have 2 chloride ions. All right, magnesium chloride dissociates into a magnesium ion and 2 ions of chlorine. I do this a lot in AP Chem when we talk about solubility equilibrium, and we're using it a lot here with net ionic equations that we're going to end up writing. So we have 2 chloride ions dissociating with MgCl2, so we would have a little coefficient there in front of it. Okay, let's go through a couple reactions, see what happens here. So what happens when NaCl is combined with MgSO4? So if you did or didn't do the lab yet, you would have a little container of salt water, a little container of magnesium sulfite solution, and you would put them together in a well tray or some other container where you mix the two together. So we have NaCl aqueous, you could write these on your note sheet if you have room for that, plus MgSO4 aqueous, and you would have your yield sign here. Okay, so NaCl aqueous plus MgSO4 aqueous yields whatever. What you truly have here is a beaker of ions, sodium and chloride ions floating around on the left, and you have your beaker or container of magnesium and sulfate ions, and they're just bopping around doing their thing. All right. What we're going to do here is put them together. So we're going to look at our 2 beakers, combine them, and see what we can do with our ions. See if any of them come together. So here we go. Chemical reaction is going to try to occur here. So this is you taking the 2 different containers, combining them into one. And let's go through ion by ion and see if any interactions are going to occur. So would you expect these 2 ions to combine, Na+1 and Mg+2? Well, of course the answer to that is no. They're not going to combine because both of them are positive charges. So like charges repel. Not going to work. Let's look at our next combination. Next combination is chloride and sulfate. Would chloride and sulfate combine to create anything? Let's take a look at it. Of course not, because both are negative and like charges repel, so it's not going to work. All right, another option, Mg+2 and Cl-1. Logic would say that, yeah, this is going to happen. We're going to have these 2 ions combine because opposites attract. Let's see what actually happens, though. Okay, nothing. So they just kind of bounce off each other. So why is that? Why do they bounce off each other when logic would say that they come together? Well, this is where that green cheat sheet you have comes into play. So if you look at that green cheat sheet, like dig it out and look at it. It's really, really important to look at that right now. You want to find magnesium, and you want to find the chloride. Like you want to find those 2 ions. So find magnesium, find chloride. So one's going to be on the left-hand side of the note sheet. One's going to be on the right-hand side of the note sheet. All right. So find one of them that's here, one of them that's here, and then follow it to where they meet in that big grid. Okay. And you want to take note of what's there. All right, so if you find magnesium, Mg+2, and chloride, Cl-1, you're going to notice that it has an S on that cheat sheet. If you go up to the top of the cheat sheet, there's a little key right here that I'm shading in on the slide here. That key tells you what the S stands for. Okay? The S stands for soluble. So that means magnesium chloride is soluble in water, which means it's not going to come together. All right, it's not going to come together. It's not going to form a precipitate of any sort. They remain dissociated. All right, so that's how we read that cheat sheet. Now we'll get to some other ones in a second here. Let's take a look at another combination though. We have sodium and sulfate. So before I advance the slide, look at your green cheat sheet. Okay, so again, here's your green cheat sheet. Find sodium, find sulfide, wherever they may be, and see what it ends up in that grid. What do you end up with? If you look at it, you should see that these are also an S. And remember, when you see that, go up to the key up here, all right, and figure out what that means. So S means soluble. So should these 2 ions combine? Take a look at it. Okay. They just bounce off of one another. So since Na2SO4 is soluble, they stay dissolved. So we went through every single combination on in this container here. So if you're in the double replacement lab, like you're doing that lab, or you're just doing any sort of worksheet or homework or test or quiz, all you end up with here is a beaker of ions. Okay, so nothing wants to come together. So you have all these ions floating around. They're bopping around, just doing their thing, and that's it. So all combinations are soluble. So what you'll end up with is NaCl aqueous plus MgSO4 aqueous yields basically the same thing. NaCl aqueous plus MgSO4 aqueous. Just a beaker full of ions. we write that as no reaction. Okay, that is really important. All right, so you clearly see that being made here on the slide. So on your note sheet, make sure you recognize why this is a no reaction. It's because all combinations are soluble. Every single thing would be aqueous in our chemical reaction. So say you did a double replacement reaction and you did rewrite NaCl, or I'm sorry, you write Na2SO4. Like let's say you did try to have this reaction occur. You would have Na2SO4. You would also have MgCl2. Like those would be your products. But you look at your cheat sheet and both of them are aqueous. When every single thing is aqueous, 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 it's simply a no reaction. All right, so that's what you want to make sure you focus on here. If it's a no reaction, you're done. You don't have to do anything else. All right. Let's take a look at another one, though, that's not going to be a no reaction. So what happens when calcium chromate is combined with magnesium sulfate? So again, if you look at your green cheat sheet, find calcium and chromate and see what you end up with. You're going to end up with an aqueous, right? The grid will say S for soluble, and then that means it's an aqueous solution. So that's good. Like the calcium chromate, you see the beaker of that here, that beaker of ions floating around. They're not combining because they're very soluble. Look at the same thing, do the same thing for MgSO4, for magnesium sulfate. Look at your green cheat sheet, find magnesium, find sulfate, and you're going to see that it says S in the grid. Again, S stands for aqueous. You got to go back up to the key at the top so you can see what you write in your chemical equation. Right? When you see an S in the grid, you are not writing an S in your chemical equation. That's really important. You got to go back up to the key and see what those stand for. Okay, so we have a beaker of ions, calcium and chromate, beaker of ions, magnesium and sulfate. Let's combine them, see what happens. Okay, let's go through our list again. Let's see if we could have calcium and magnesium combined. They're both +2s, not going to happen. Let's go through and find some other combinations. Let's look at chromate and sulfate. They're both -2s, not a chance. Okay, next option, magnesium and chromate. So what you want to do is, like this looks good, right? Opposites do attract. Looks like this would occur. Let's take a look at our green cheat sheet and tell me what you end up with in the grid when you find magnesium and you find chromate. Well, if you find the two of them, wherever they are, meet in the middle somewhere, and you're going to see that magnesium and chromate give you an S on your cheat sheet. So you go up here to the key, and S, again, for the 10th time here, is soluble. So should those combine? The answer to that's no. Right. Looks like they should, but they don't, because they bounce off each other due to them being soluble. All right, so they stay dissolved. All right, last hope. We have calcium and sulfate. So do the same thing. Go to your cheat sheet, find calcium, find sulfate, meet in the middle somewhere, and what do we end up with? If you look at it, you should end up with something that says I. Well, if you look at your key on your cheat sheet, I stands for an insoluble precipitate, which means it is a solid. All right, a precipitate is a solid that doesn't dissolve. We talked about that way back in Unit 1. All right, so we actually do get a precipitate. We do actually have a chemical reaction here. So if you're in the lab doing the double replacement lab and you see something occur, like a precipitate occurring, or sometimes a liquid or a like a different liquid or a gas occurs. That's a little bit rarer. But if you see that solid precipitate, the chemical reaction occurred. This is what's happening. Calcium and sulfate combine in a way that they are very insoluble. So they would rather stay together and create that insoluble solid, that precipitate, then they would prefer that over staying dissolved and moving around in solution. So the visual representation here is really important for what's going on. You have your solid precipitate that is now settling at the bottom of your beaker. Okay. In addition to that, you have a bunch of ions floating around. So let's go through and actually see, how do we write all this? What are all these steps on our chemical equation, or of our chemical equation, that we need to do for double replacement reactions? So here's the start. Calcium chromate plus magnesium sulfate. Automatically switch your positive ions. So you're going to make magnesium chromate and calcium sulfate. Okay, so that is known as your regular chemical equation, your first step, your formula. All right. look at what we did. This is required for these. I'm a little more lenient with the other chemical reactions. I'm not lenient at all when it comes to double replacements. And maybe the picture of me is in the way here, so I don't know if I can move that out of the way. Yeah, look at that. Okay, so I moved me out of the way so you guys can see what I have here. So make sure calcium sulfate has the S next to it. That's solid, all right? Because that's your precipitate. That's the I, insoluble, on your cheat sheet. What we want to do now is take everything that's aqueous and break it apart, okay? So the next line in our notes should be an ionic equation, okay? So here's your regular equation, that first line. Now I want to see what all of the ions are. So pay attention to this part of it. Calcium chromate is soluble, so it dissolves into calcium +2 and chromate -2. So you have to show the charges here. Ions, okay, we're in our ionic section here, our ionic equation. Ions have charges to them. This is why nomenclature is so important, okay? So as I've already talked about a million times, calcium, Ca+2, chromate, CrO4-2. The next thing you're going to look at is magnesium sulfate. It's aqueous. Since it's aqueous, it will dissociate. You're going to get Mg+2, SO4-2. All right? So again, we don't have charges in our first equation. We do have charges in the equation afterwards. Let's look at the next one. We have magnesium chromate. There is an aqueous here, so you do break that apart. Mg+2, CrO4-2. Lastly, let me move me back up here. Okay. Lastly, we have calcium sulfate. It was a solid. Look what you do. You bring it back down as a solid. You do not break up calcium sulfate. You don't break it up because look, you have calcium sulfate precipitate here. They're not ions. They're together in a precipitate solid form. If the ions were floating around up here, then yeah, you could write it as calcium +2 sulfate -2. But if a chemical reaction occurs, you're going to end up with something in your ionic equation that is not aqueous. In this case, here it is. Here's our solid precipitate. The next thing we want to do is figure out what ions are just hanging out and not doing anything, and which ions are actually involved in the chemical reaction with the product we are creating. All right, so that is our last step. You want to look at ions on both sides, okay, ions on both sides, and circle them. All right, so I have a chromate on both sides. I see a CrO4-2 and a CrO4-2. Circle them. Is there anything else that you see on both sides? There should be. You should see a magnesium on both sides. We're going to circle them. Those are known as spectator ions. Okay, so make sure you label that on your note sheet. Spectator ions are these guys floating around here in the beaker. Spectator ions do not take part in the chemical reaction. Just like if you go to a football game and you're in the stands watching it, you're a spectator. You're not playing the game. You're spectating. You're a spectator. You're not taking part in the end result of that game. These spectator ions are not taking part in the end result of our chemical reaction, which is creating that precipitate. So what we do for our last and final step is we take our spectator ions out, all right? And what you will write underneath is this. Okay, this is called your net ionic equation. Okay, the net ionic equation is your ionic equation without your spectator ions. So the only ions involved in making the precipitate here are your calcium ion, your sulfate ion, producing calcium sulfate. So look at the detail here. Ca+2 plus SO4-2 yields CaSO4. These are worth 8 or 9 points on a test or a quiz because you got to do so much work that's involved here. So you have to show the formula, you have to show the ionic, you have to show the net ionic. This is the process you go through. Green cheat sheet tells you what these states are up here, which tells you how you proceed through the rest of the chemical reaction. So that's our end result here for this, which is the formation of our precipitate. Okay, let's give one a try here. Let's do one more. I'll try to kind of walk you through it here a little bit, and we'll see what we end up with. So you can pause the video or take a look at it and see if we can figure out how to do this. Then I'll go over it together as a group here. All right. So we always start with our word equation, right? So we have potassium phosphate and barium chloride. You recognize this as a double replacement reaction. So what you need to do here is just automatically switch your ions and write out what your product is going to be, or what your products are going to be. So let's take a look at it. We have potassium phosphate and barium chloride. Let's flip our two positive ions and write some products here. All right, so the products are going to be, our proposed products will be barium phosphate, sorry with the handwriting, and potassium chloride. Okay, the next thing you want to do is go to your green cheat sheet. Okay, before we do all that other work, let's see if this reaction actually occurs. So you go to your cheat sheet, you find barium, you find phosphate, and what do you get? You should see on your green cheat sheet that when you combine barium with phosphate, you get the letter I. Remember, go up to your key at the top, and the letter I is a solid precipitate, so you put a solid next to barium phosphate for your state of matter. Do the same thing for potassium chloride. You find it, and you should see that it is an S on your cheat sheet. S. Go up to the key. S means soluble. Okay, so that's why some students get confused by this. Like, why can't I put S in the chemical reaction? Because S in the grid means soluble, which means AQ. Okay, so now you ask yourself if this reaction occurred or not, and it did. Okay, so it does occur because we have something that's not aqueous. All right, so if everything here was aqueous, it's over. It's a no reaction. You move on with your life and go on to the next one. But because we have a precipitate, the reaction does occur, so we have to make sure we go through the rest of the process here. So let's go through and do that. The first thing we should do after this step is write our chemical formulas. So I'll do that for you real quick. We have K3PO4 aqueous plus BaCl2 aqueous yields barium phosphate Ba3PO4 solid plus potassium chloride KCl aqueous. Yours needs to look exactly like this, okay? If you don't have the states there, it's wrong, okay? If you don't, like, we have to balance it, obviously. If you don't have it balanced, obviously it's wrong. That's our next step here. Don't be lazy. Put the states of matter there. All right, students always tend to forget the states or just not worry about it here. It needs to be next to every single thing in your chemical reaction for double replacement. No doubt about it. Okay, so if it's wrong or if it's not there, it's going to be marked wrong or some points will be taken off for that. So to balance it, it's pretty straightforward. We're pretty good at balancing by now. Actually, we're not going to need that there. Looks like we're going to have a 6 there instead. There we go. And 3 here. 1 there if you wanted to. And now we look good. Right? 2, 3, 1, 6 for your balanced chemical equation. All right, the next step is the same every time. We got to go through and take our aqueous solutions and break them apart. So this, I chose this example on purpose so we can go through, because the ones in the earlier part of the lecture didn't have any coefficients. The equations were balanced already. So look at your potassium. You don't have 3 of them. You actually have 6 of them. So what you end up doing is down here, you have 6 potassiums. All right. How many phosphates do you have? You have 2. All right. So look at your coefficient and multiply that by what you have in the formula itself. That's how many of those ions you have. If you had K3PO4 and you dissociated and you had 2 of those dissociating, you'd have 6 potassium ions floating around and 2 phosphate ions floating around. All right, let's do the same thing here. How many bariums should we have? It's 3. And how many chlorides should we have? It's 6. Students get confused by this. You're like, well, Cl is by itself. Why isn't it Cl2? You got to pay attention to the details here. Chloride is different than chlorine. If it said chlorine, okay, CHLORINE, of course it'd be Cl2. But we have a chloride, okay, IDE ending, we have the chloride ion. Okay, that could be by itself, obviously, because it's not chlorine. So we have 3 times the 2 that are there. 6 of those would be floating around. Now this is important. Remember, I talked about it earlier in the lecture. We have Ba3PO4 2. It's a solid. It does not dissociate. just bring it down as is. Ba3, PO4, 2, solid. Plus 6 potassiums and 6 chlorides. Okay? Next step in the process, you want to find your spectator ions. So find ions on both sides that are exact matches. If you balance your equation first and you bring your ions down correctly, it should match up perfectly. Look, 6 potassiums, 6 potassiums. If I screwed up and had 6 potassiums on the right and only brought down like 3 on the left, something like an alarm goes off in your head. Go back up and take a look at what you did and you made a mistake balancing or formula writing. Okay? Looks like we also have 6 chlorides. Cross them out. Those are your spectators. Final equation is your net ionic. Bring everything else down, and it should make sense when all is said and done. So bring down 2 PO4 negative 3 plus 3 Ba plus 2 yields Ba3 PO4 2 solid. That state comes down the whole way. Solid, solid, solid. Gotta be there. Okay, no doubt about it. No excuses for that. It all makes sense now. Look, you have 2 phosphates, 3 bariums. 3 bariums is perfectly balanced, so it works out the right way. Really, really nice once you work it out and get to the end. Students usually like these ultimately once they figure out what's going on after a couple of practice problems. They say it feels really satisfying because it just kind of works itself out at the end, and it's really nice when everything kind of falls into place like that. Okay? So I know this is a longer lesson, but double replacement reactions take a while to understand and to know what's going on here. So let's try to wrap it up a little bit with one last useful tip, and that is with acids. So we'll talk more about these in class in person, but I don't want acids to bully you. So students tend to see an acid and they start to be very confused and they don't know how to approach the problem. To take away the bullying power of an acid, you want to call it by something, it's called its nerdy name, all right? So of course that's what you would do when somebody's bullying you, call them by the nerdy name. That'll solve everything. So for example, hydrochloric acid is HCl. Students see HCl, or they see hydrochloric acid, and they don't know how to approach that because they don't know, like, if it's in a double replacement or single replacement reaction, what's going to switch. Well, you want to call it hydrogen chloride. Then you could easily see if something's going to react with that. The hydrogen is the positive ion. That's what would switch out. Okay. Another example is sulfuric acid. Students see that, they're like, how do I name this? What do I do? Just call it hydrogen sulfate. If you rewrite acids with their nerdy name, then it takes away that bullying power, and it's easier for you to see what's going on. All right. So you can work through some of the double replacement reaction homework, or maybe some parts of the lab. Depends on where we are in class right now. But we'll talk more about this in class, review a little bit. If you're still having a hard time, we'll take it from there. All right. Thanks, guys.